Hello, welcome again. We are solving GATE 2018 Aerospace Engineering paper. The question number 45, 35 is a rocket has initial mass of 150 kg. After operating for a duration of 10 seconds, its final mass is 50 kg. Acceleration due to gravity is 9.81 meter per second square. The thrust produced by the rocket is 19.62 kilonewton. The specific impulse of the rocket is option A 400 second, option B 300 second, option C 200 second, option D 100 second. So specific impulse is ISP, specific impulse is F by m dot g. Okay, where m dot is mass for it and g is acceleration due to gravity. So F is thrust produced by rocket is equal to 19.62 kilonewton. 19.62 kilonewton. Okay, and m dot mass of fuel per second is initial initial mass is 150 and final mass is 50. So mass per second and time for this reduction in mass is 10 seconds. So mass of fuel per second is 150 minus 50 by 10. Okay, that is 10 kilogram per second. And g is 9.81. So specific impulse is 19620 divided by 10 divided by 9.81, that is 200 seconds. So answer is option C. Next, consider the vector field V is equal to minus y by r square I plus x by r square j, where r is root x square plus y square. The contour, the counter integral, this counter integral b vector v ds, where ds is a tangent to the counter, to the contour that encloses the origin, is equivalent to 2 results. So as r square is equal to x square plus y square, so let x is equal to r cos theta and y is equal to r sin theta, and theta varies from 0 to pi for the enclosed origin. So because it is enclosed to origin, so theta will vary from 0 to 2 pi. And differentiating with respect to theta, then dx will be minus r sin theta d theta, and dy will be r cos theta d theta. And now we can put this y and x in this equation. So we will be your minus sin theta by r plus I plus cos theta by r j. So minus y by r square dx plus x by r square dy. So circular integral will be like this, and it will be y by r square is your sin square theta, sin square d theta, and x by r square d theta, theta is your this quantity. So dy is your r cos theta, and this is your r sin theta. X is your r cos theta. Okay, so it will be cos square theta and it will be sin square theta, and theta will be. Okay, so now we can change this as a common statement. So it will be 1 sin square theta plus cos square theta is 1, and it is varying from 0 to 2 pi. So put in the limit, that will be 2 pi. So answer is 6.2. Okay, so answer is 6.2. Next, the magnitude of the x component of a unit vector at the point 1 1, that is normal to equipotential lines of the potential function phi r, is equal to 1 by r square plus 4, where r is root x square plus y square, is dash equal to 2 raised to base. Phi r is equal to 1 by r square by r square plus 4, and as this is your potential function, so velocity in radial direction is curly pi by curly r, that is minus 1 by r square plus 4 square into 2r. Okay, so that is the velocity in radial direction, and velocity in circumferential direction is 1 by r curly pi by curly theta, and curly pi by curly theta is because this is not the function of theta, so it is 0. So it means there is no circumferential velocity and there is only radial velocity. So this may be either a sink flow or a source flow. And for sink flow and source flow, the equipotential lines are a circle around the origin, and if these are the circles, then these lines will be your stream function lines. If it is this is the point on the equipotential line is 1 1, then the unit vector perpendicular to the equipotential line is, because x is 1, y is 1, so x is putting x is equal to 1, and the magnitude of this vector is x square plus y square. Okay, and because this is your 1 and 1, this is the magnitude of this, and x is this. Okay, so magnitude of unit vector is 1 by root 2. Okay, so this is 1, this is 1, this is 1, so answer is 1 by root 2. Next, assuming ISA standard sea level conditions, 288.16 Kelvin, density of 1.225 kilogram per meter cube, G is equal to 9.81 meter per second square, R is equal to 287 joule per kilogram per meter. The density in kilogram per meter cube of air at Leh, which is at an altitude of 3500 meter above the mean sea level, is accurate to 2 raised to the h. So rho by rho 1 is equal to E minus G naught by RT bracket H minus H1. So H minus H1 is 3500 mm. Okay, so H minus H1, because height altitude is given as 3500. So and G is 9.81, R is 27, T is 288.16, and density at sea level is 1.225. So we can find out density at height of 3000 meters. So solving this, we get 0.8582 kilogram per meter cube. Okay. Next, consider a cubical tank of size 2 meter with its top open, is filled with water up to a height of 1 meter. Assuming the density of water to be 1000 kilogram per meter cube, G as 9.81 meter per second square, and atmospheric pressure to be 100 kPa. The net hydrostatic force in kilonewton on the side face of the tank due to the air and water is dash accurate to 2 resolution. So this is your tank, and this is here atmospheric pressure, here there is atmospheric pressure. So here is the atmospheric pressure, here there is atmospheric pressure. So this pressure is varying from this place to this place, or to this depth in a linear fashion. Okay, so here the pressure is atmospheric, so here the pressure will be rho gh. Okay, and atmospheric pressure will cancel out, so the change in pressure will be this pressure. Okay, so net force acting on the side of the wall is area of the wall. So net force per unit weight is rho gh into rho gh. Rho gh is height into h by 2 So rho is 1000, G is 9.81, h is 1. Okay, so this is the force per unit width, and if width is 2 meters, then the net force is multiplied by 2. So answer is 9.81 kilonewton. Next, an aircraft with mass of 400,000 kg cruises at 240 meter per second at an altitude of 10 km. Its lift to drag ratio at cruise is 15. Assuming V as 9.81 meter per second square, the power in megawatt needed for it to cruise is equal to 2 raised to 6. So power at cruise is W by CL by CAD into V, and W is given as 400,000 into G. Okay, and CL by CD is 15, B is 240. So answer will be 62784 or 62.784 megawatt. Okay. So that is the power required during cruising in terms of weight. Okay. Because from this we can lift into, or thrust into the